Hey Hawks. So today we're going to talk about moment of inertia. Um, if you're comparing this to regular mechanics, this would be like the mass. Okay, so it's kind of like the mass of a rotational object. So I will explore how forces, torque, and kinetic energy interact to describe rotational dynamics, applying these concepts to explain the behavior of rotating systems in physics, engineering, and real world technologies. Okay, so in linear dynamics, the mass of the object plays an important role. During rotational dynamics, it's not just the mass, but also how it's distributed about the center of rotation. This is called the moment of inertia. The moment of inertia of an object is how hard it is to change the rotational speed of an object, right? So if you have a bike tire and it's spinning and it's in your hands, it's hard to get it to change its axis of rotation. Okay. Note the axis of rotation is a line that is 90 degrees to the plane of rotation. So this Z right here, this is its axis of rotation, just like this one. Okay. All right. When a point mass rotates in a circle about an axis that is perpendicular or 90 degrees to the motion, the moment of inertia is given by the formula I stands for inertia, equals m, the mass of the particle, times the radius squared. And it's basically how far from the center of the circle to the particle. Okay. So r is the distance from the axis of rotation. When there's more than one mass, the moment of inertia is calculated by adding them together, just like with forces, right? The sum of the of each inertia is equal to the net inertia. Okay. So if you had 3-point masses, then you would produce a moment of inertia that's m1 times r1 squared plus m2 times r2 squared plus m3 r3 squared. Okay. The masses could be different, the radiuses could be different. Okay. It just depends. The good thing is that usually the formula for inertia will be given to you. Okay. So when the distributions of mass spread out like a disk, calculating about amount of inertia becomes a little bit more difficult. So instead of individual particles, now we have a whole particle that's flat. Okay. So there are basically 5 shapes that we work with. There's the sphere, right? So you have a sphere, which is basically a ball and it's rotating. So you can kind of think of it like the Earth. There's the disc. And the disc is, it's like a flat circle, like a small cutout of a cylinder, right? And that's spinning around. Then you have a rod, right? So you have like a rectangular piece of metal that's spinning. And then you have another rod, but this time instead of spinning this way, it's spinning this way, right? The whole length of the rod. And then you have hoops. Basically, hoops are hollow cylinders. Okay. Like I said, the moments of inertia will mostly be given to you. You do need to know how to handle a point particle, but most of these other ones will be given to you. Okay, so what have we learned? Well, we learned that during rotational dynamics, it's not just about the mass. It's also about how that mass is distributed about the center of rotation. The moment of inertia of an object is how hard it is to change the rotational speed of an object. The moment of inertia is given by I equals m times r squared. And remember that the net I is the sum of the i's. And then IB will provide you the moment of inertia for those 5 basic shapes.